So this is chapter 2. Chapter 2 is about sets and a little more work with logic. We've already seen a little bit with the idea of deductive reasoning, inductive reasoning, excuse me. And then in this chapter, we're going to take a look at deductive reasoning along with sets. Section 2.1 is all about the idea of a set. And in my opinion, when we think about math and we wonder, like, what's the most basic thing we do with math? And I used to think it was, well, counting, right? My kids learned to start counting stuff. They learned to say 1, 2, 3, 4, 5. But it turns out they were counting before they learned to say 1, 2, 3, 4, 5 or write 1, 2, 3, 4, 5. And they learned about that through the idea of sets. So a set is just a group of things. And there's lots of different groups of things, right? So for example, I have the group of colors in my toolbar. So I could describe those colors and then I could show somebody those colors. I could write them down as a list. When we write sets, we usually use curly brackets when we list the elements of a set. So my colors up there, my toolbar are black, red, blue, green, and yellow. Other sets, my favorite letters today. And today, my favorite letters are Z, A, and E. Why? I don't know. I like those letters today. Z is a great letter, doesn't get used a lot. A is awesome. It's like the @ sign also. That's pretty cool. And E, it's the most common letter in the English alphabet. Are there other cool letters? Yeah, but these are my favorites today. So sometimes there's a clear reason why there's things in a set. Like you can see right here, the colors in my toolbar up at the top on the left. My favorite letters, in some ways that's kind of a random thing, but it's a set because I made it one. Another example, set of dogs in my house. At the moment, that set is empty. My dog died a couple years ago, haven't got around to replacing him yet. Dog's a big commitment, I'm not ready for that. I have teenagers, that's enough. So in this case, I can describe a set and there's nothing in the set, and that happens sometimes. So just note this set is empty. And I mentioned that kids learn about counting way before we do things with them, like count 1, 2, 3, 4 as words or as symbols, because they recognize when there's 2 people in front of them or just 1 person in front of them or no people in front of them, right? They're just naturally observing and counting, even though they're not using the same language as we are about it. It's just this experience for them. So sets are an experiential thing. And based on sets, we get numbers. How do we get numbers? Well, this set has nothing in it, so it's related to the idea of 0. Right? It's empty, there's nothing in it. That's one way we use 0 in mathematics. This other set here with the Z, A, and E, it's related to the number 3. And sometimes we write this symbol for 3. Mine's a little messy there. Sometimes we write the word 3. The set of colors in my toolbar, there's 1, 2, 3, 4, 5 colors. So this is related to the number 5. So the number of elements in a set is called its cardinality, and that's the beginning of the idea of number. But sets are more basic than that. And we just want to explore sets before we explore numbers some more. So we have this general idea of set. And it's just this group of things. What's a thing? That's a tough question. What's a group? A group is a set. What's a set? A set is a group. Okay, can we use another word? Yeah, we could use the word collection, but then somebody says, okay, what's a collection? Well, a collection is a group. Ultimately, you have to show somebody. So ultimately, this is some kind of an experience. And we know what it means based on experience. And a lot of our lives are just that way. Now, in a set, there are elements. And elements are the individual components of a set. You can't break them down any further. And language is a little bit tricky here. Earlier, instead of group, I used collection. But then somebody says, what do you mean by collection? I would say, well, I mean, it's a set. So ultimately, I just got to show you, well, this is a set, and that's a set, and this is a set. Element, those are just the individual things. What do you mean individual? Well, they're the smallest things in the set. What do you mean smallest? Well, they're the individual things, right? Ultimately, I just got to show you what it is. So sets are kind of a little squirrely that way, but it's an important idea. So the individual things in a set. And then I mentioned the earlier, if we count those individual things, that's called the cardinality of a set. And a cardinality of a set is simply the number of items in the set, the number of elements in the set. And some sets have no elements, that's fine. They can have no elements. Some sets have one, some have two, some have more. That's all over the place. So this, again, is an important idea. Cardinality of a set is just count how many elements in a set. So I might say, usually when we're talking about sets, we often abbreviate them. We give them a name, like maybe set A. And set A, maybe it's my colored set before where I had black, blue, green, red, and yellow. So I can talk about a set by listing the elements in the set. I can describe the set in words. They are the colors in my toolbar, in my virtual paper, on my laptop. A set needs to be clearly defined so that we can all agree what's in the set and what's not in the set. Right? So I can look up here and I can see purple's not in my set. I can look in the list down here and see purple's not in my set. When we're talking about the cardinality of a set, we'll often put a little n in front, parentheses, and then the name of the set, which basically says what's the number of elements in that set. So if you see something like n parentheses a, you just look at the set and count. 1, 2, 3, 4, 5. So the number of elements in set A is 5. Five, right? This is a numeral representing the idea of 5. So just kind of a bigger scheme of mathematics here. We have this basic idea of a set. And then we can count the elements in a set. That's called the cardinality. That cardinality, right? That's a count. And that is basically an idea, right? The basic idea of number. So I had my set A, which had my 5 colors. I could make up another set. Let's call this set B. And in there I have A, B, C, D, and E. Make a set C. And then in set C, I'm going to put exclamation point, the @ sign, the pound symbol, the $sign, and the % symbol. Now, my original set A, set B, and set C, they all have something in common. They have the same cardinality. Right? They have the same count. When sets have the same count, we say they're equivalent sets. There's lots of terminology here. Oops. Wrong letter. When sets are equivalents, we also say they have a one-to-one correspondence. One-to-one correspondence mean if I line them up and I keep them in order, like above here, the first element is A here and the first element is exclamation point. So a correspondence means to relate them to each other. So I'm going to relate the B in the @, I'm going to relate the C to the pound, I'm going to relate the D to the $sign, and I'm going to relate the E to the % symbol. And all the elements in set B are accounted for. All the elements in C are accounted for. There's nothing that was used more than once. There's nothing that was missed. And when you can do that to a set, that's called a one-to-one correspondence. That means they have the same cardinality. That means they're equivalent. Now they're not equal, right? They're different things in there. B is a different set than A. Somebody might say, well, what about this set? Let's call it set D. And they say their set is E, D, C, B, A. And I would say to them, that's the same set as mine right here. You just wrote them in a different order. The order you write them doesn't matter. It's not like a list of numbers. It's just you have this collection of stuff. So I have this bag. Inside my bag, I have these letters. What letters are in your bag? Well, I have the letter C and the letter E and the letter D and the letter B and the letter A. Order doesn't matter per set. It's just you have a collection of stuff. So in this case, D and B are more than just equivalent. They don't just have the same number of things. They have the same exact things. So that's a slightly different idea. So in this case, I would say sets B and D are equal, meaning they're exactly the same. Equivalent with sets just means they have the same count. So big ideas, we have the idea of a set, collection of stuff. Sets have elements. We can count those elements. The count of those elements gives us the idea of number. If the sets are the same size, they have the same cardinality, the same number of things, we say they're equivalent, and we can make a one-to-one correspondence. And it turns out you can make lots of one-to-one correspondences to the sets. I just happen to choose the easiest way to do it, which is to match up the first ones and the second ones and the third ones and the fourth ones and the fifth ones, but I could have done it a different way. That's a whole nother question. More in a moment.